So to get some of our redox demos started, we've invited the Redox Genie to join us today. So when I open the top to the bottle, with a little bit of luck, the Genie will come out and we'll know we're good. So you can see the Genie on the bottle. Probably gonna get sued by Disney for this, aren't I? And we also have I Dream of Genie, Barbara Eden from the 60s TV show. Sort of a fun fact, on the show, she was not allowed to have her belly button shown. The censors would take that out. I assume they thought this would lead to dancing or something like that. So let's see if the Genie wants to make a visit, okay? Ooh, the Genie has arrived. Genie is making quite a mess. Looks like Mr. Gottlieb should have measured something instead of estimating. These things happen. Well, it's okay. At least I don't have to call and ask for another ceiling tile like I did once. And on your lab sheet, on your worksheet, you'll answer a few questions, and there'll be question 5 on the handout. I know they're out of order, but that's okay. And that one's done. Apparently we're being invaded by mini gummy bears. They're just all over the place. And I'm not happy with that. I've captured some of their friends, and I'm going to try and get them to tell me what their invasion plans are. So what I'm going to do is show them what will happen if they don't talk. So I'm going to put a couple of them here so they can get a good view. I'm going to put the ones I captured in this dish of glucose and potassium chlorate. Okay. The hot plate, by the way, is not on. The hot plate is just to elevate it a little bit. The green light just indicates it's plugged in. So in here I have some glucose, C6H12O6, not table sugar, which is sucrose, and some potassium chlorate. You'll figure out the oxidation numbers of the relevant atoms. The reaction won't go without a little kickstart of some kind. What you might have learned is the activation energy. I could heat it, but it's generally not a good idea to heat anything with chlorate ions. So I can catalyze this reaction with a drop of concentrated sulfuric acid. What essentially will happen is the sulfuric acid will dehydrate the sugar, and you'll actually see some black carbon left at the end, but it will also be highly exothermic, and that'll get the reaction going. So let's see if we can get these gummy bears to talk. It ignited its neighbor. Okay, it wasn't quite my plan, but that's okay.
Oh my God.
That was pretty impressive.
That was pretty impressive.
So let me hold this up now, and this is extremely hot.
Oh my God.
Well, there's the carbon.
Stay still while I zoom in.
And it actually smells like we're roasting marshmallows in here, because marshmallows are sugar. All right, I got a lot of cleaning up. Okay, this is just one of my favorite demonstrations. I'm going to take a Erlenmeyer flask, and this is reaction 2 on your handout. I'm going to pour 30 milliliters of aqueous silver nitrate solution in. I've pre-measured this. Then I'm going to add ammonia, and I'm going to add it drop by drop until I make what's called a complex ion. So first I'll make the brown precipitate silver hydroxide, and then when I add more ammonia, I'll make what's on your handout as AgNH3 parentheses 2 plus 1, which is colorless.
Keep it still.
So you notice I'm forming a brown precipitate, and what I want to do is I want to add enough ammonia to just dissolve it. So since I don't know exactly how many, you can see it's almost dissolved. Give it a shake and a couple more drops.
Not
Looks
quite.
like one more drop will do it. Looks like a couple more drops. Cooperate. Feed you to the gummy bears. There we go.
Perfect.
Okay, put the lid back on. Now I'm going to add some sodium hydroxide. And then after that, I'm going to add some glucose. This has to be done rapidly, and now I'm going to shake it. And it'll take a little bit of time, but with luck, what will happen is the silver ions that we formed originally, and this is nothing to sneeze at, Ms. Valatek. The silver ions that we formed originally will end up undergoing a redox reaction and become solid silver. And the silver will deposit on the inside of the flask with a little bit of luck. I have to use a brand new flask that's clean. You can almost see a little silver. This is called a test for reducing sugars. Sometimes it's called Tollin's test. And this was actually the old way to test for glucose in diabetes. They would actually take somebody's urine, put it in, and if you got the silver mirror, you did. That, of course, was a dramatic improvement over the original test for glucose, which was the taste test. So what we're going to do in this demo is essentially the original breathalyzer test. The breathalyzer test originally was a color-changing reaction that would show if you had alcohol on your breath. Nowadays, there's essentially a mass spectrometer in the car. So I'm going to take some potassium dichromate, and the chromium in this oxidation state is orange. On the worksheet, this is demonstration number 1. And it asks you to figure out the oxidation number of the chromium, so obviously I won't be doing that. So you can see this is orange. This is ethanol. This is what is commonly called alcohol. If you're going to take biochem from Ms. Valatek, you'll learn this is a primary alcohol. And this is essentially the only alcohol that could be on your breath for any reason, okay? Any other alcohol you consume, you would not be driving.
Period.
You wouldn't be doing anything, quite frankly. Yeah. So let's put some in, and you'll figure out the oxidation number of the carbon. And when this reaction happens, give it a little shake, you'll notice we get a color change because and there's a little density difference between the two. So I'll just mix it up.
Can you move it over towards the window, away from your sweater? There you go, because your sweater.
So here's the before and after. And it turns kind of a blue-green. It can be slightly different colors, but essentially you used to breathe into a tube with this soaked into like a powder, and if there was a color change, there was alcohol in your breath. It doesn't tell how much. It used to be like if you had just gargled with gobs of mouthwash, maybe there'd be enough. But for the most part, if you get that color change, you shouldn't be driving a car. So in this demo, we're going to take some ammonium dichromate and we're going to decompose it. And we're just going to use heat to decompose it. So I put some in a flask. I've put a wire gauze on top just to keep things from escaping. And you've got the unbalanced equation on your worksheet. You can figure out the oxidation number of the various chemicals. One of the products formed is water vapor, so you may see a little fogging up. It can take a couple seconds for this to happen, but you can almost see a little bit of what looks like fog in there now. And that's some of the water that's coming off. And eventually it'll get hot enough and you'll notice a color change. You'll also notice a volume change because both the water and the nitrogen produced are gases. So because gases take up much, much more space than solids, we'll notice this essentially puff up once we get the color change. Now a brief musical interlude, but not from me. Okay, we're starting to might see, I don't know, it's getting a little bit darker as it goes on, and that's a clue we're starting to get enough heat to make the reaction go by itself. You might also notice it looks like it's puffing up a tiny bit. But, okay, gonna go in just a second.
Patience is a virtue.
Yes, it is. It's also a good friend of my wife from when she was growing up. There we go. So I'm going to shut this off. But you'll notice now our solid product is clearly a different color. And you'll also notice it's taking up a very large volume. It's almost filled up the flask. And that's because we've trapped some of the gases in there that are formed. It looks like somebody's got some cleaning up to do.
Wow.
I wonder who that poor person's going to be.